We have finally made it. We are at our very last topic of study for this year, which is modern physics. So when we start, we're going to look at the very beginning of classical physics, and we look at Greek culture. So the Greeks recorded the first systematic observations of the natural world. This was the first concept of the atom, which you are definitely going to go into more in detail next year in chemistry. For now, we're going to focus on it a little bit. So we've talked about the atom and we talked about electricity, the smallest piece of matter possible. This idea of the atom being the smallest piece of matter stuck around for about 1700 years, and that's what we are going to go into more detail on in the next lesson. So, scientists gradually constructed a system of classical physics. We already talked about Newton's laws. We talked about Isaac Newton. We talked about the electromagnetic spectrum and looking at light as a wave. The classical model is complete at this point and can basically explain everything. And you see on here all of these different physicists that we have talked about this year. You saw Newton. This particular topic of study, we are going to talk finally about Einstein. So physicists in this particular era, up until this point of study, were still posed with three puzzling phenomena that they couldn't explain. So one being the photoelectric effect, which we will discuss, hydrogen bright line spectrum that we will also discuss, and black body radiation, which is very interesting. It's more of an advanced topic, but if you are interested in space or orbit or different satellite structures, you definitely will want to look a little bit further into that. So now we get into the year of 1900, which is the year that we are able to define as the year of the quantum. So Planck invents the concept of the quantum to solve the problem of black body radiation. So a quantum is a small packet of energy which acts like a particle. So when we talk about a quantum, it's a word that we use to be able to describe a larger piece. So a quantum relates to a small packet of energy, but that energy can be multiple pieces. So this accounts for the odd behavior in radiating objects using tiny constant to almost estimate the math. So we have here Planck's constant, which is on the front page of your reference table. We're going to round it to 6.63 times 10 to the negative 34 joule seconds. If you want to be more specific, you can use the thousandth decimal place. That is totally fine too. Planck was able to solve the problem, but did not like the solution because we have to estimate and almost fudge the numbers with this constant. So now finally we get into talking about Albert Einstein, and this is Einstein right here. Definitely not the normal picture you're used to seeing. Most of the time you see Einstein with like crazy hair and his tongue sticking out, looking all sorts of crazy. But this is Einstein when he was younger, obviously. So in 1905, Einstein used Planck's constant and used Planck's ideas to be able to explain the photoelectric effect. And this effect says the electrons in metal are liberated or freed by packets of energy, these quantums of energy in light. Light is made up of particles called photons, not protons. Protons relate to electricity, but photons like a photo. Photons are particles of light. So we have this new equation here, which is the energy of a photon is equal to Planck's constant, which is our letter H, multiplied by frequency, which can also be equal to h times c, which is the speed of light, divided by wavelength. So again, it just totally depends on what we're given in the problem, what constants we have to be able to go through and solve. Okay, so what is the energy of a photon with a wavelength of 4.5 times 10 to the negative 7 meters. Well, we're looking for energy. We know that we have a photon, so that is very specific in terms of where we're looking on the reference table. This happens to be on page 5 of your reference table under the modern physics equations. So they give us wavelength. We are looking for energy. The formula that we need to use is E equals hc divided by wavelength. Remember, h is a constant, and I already told you that we're going to round the 6.63. So again, if you want to use 6.626, you can. Your value will be very close to mine. Multiplied by the speed of light, divided by the wavelength that is given, and we were able to solve for the energy of the photon. What is the frequency of a photon with an energy of 7 times 10 to the negative 3 joules? Well, now here you're looking for frequency. So we have energy. We're looking for frequency. Again, you're going back to your modern physics formulas. Remember, h is a constant. So we're able to use E equals hf, plugging in, dividing correctly, making sure you're using parentheses. You should end up with 1.06 times 10 to the positive 31 hertz. So now this takes us to what Einstein is probably most noted for, which is his theory of special relativity. And for this, Einstein concluded that mass and energy are basically the same thing. And to do this, he used his most famous formula, which is E equals mc squared. If people have no idea about what physics is or don't know anything that you study in physics, they definitely do know E equals mc squared, even though they have no idea what it means. So finally, it took the entire year for us to finally get to probably the most noted equation in all of physics. So E equals mc squared. E is your energy of a photon. Mass is obviously mass in kilograms, and c is still the speed of light. Notice for the equation, squared goes with the c, not the m, so it's mass times the speed of light squared. So just be careful when you're doing the math. So how much energy would be released if 3 kilograms was completely converted into energy? Well, when you're doing these problems, it's very clear as far as what is given to you, right? So they tell you that you have energy and you want to know, or you're looking for energy, and you want to know what happens when you only have 3 kilograms of mass. So if you're looking through your equations, you want to know what equation will give you energy if all you have is mass. And the only equation that directly converts mass to energy or energy to mass is E equals mc squared.